Okay, now recording has started and we should be able to retrieve the recorded lecture. All right, so I have shared my screen so you can all see the PowerPoint slides. The first PowerPoint slide.
Yep.
Okay, very good. Then I just welcome you all officially to this course, Solid State Chemistry. So maybe before we start actually with the course material, let's go through a few organizational aspects. So I have decided to teach that course online for safety reasons and also for flexibility reasons. So we'll have these live sessions, but I will also record these live sessions and I will upload them into Google Drive and I will give you access to the respective file. Unfortunately, I cannot load the file into CoreSite because CoreSite restricts the file size, and these video recordings just get large very, very quickly. So I will load them into Google Drive and give you access, and you can download all the recordings from there. Yeah, so you're invited to ask questions during the lecture. Maybe mute your microphone as long as you do not want to say something. But when you want to say something, just unmute it and then say something. I think that will go everything more smoothly, so any unintended noises just don't appear during the class. So you can ask these questions during the class, but at the end of the class, we can have a little extended Zoom session if anybody thinks, well, something is worth a discussion directly after the class. So I will stop the recording then, and we can have these informal discussions then directly after the class. You can also ask me questions by email. You can make office appointments. So if you want to meet me in person in my office, then I would offer you that. Please make, in this case, an appointment by email. So send me an email saying that you would like to meet me in person, then we will meet in person in my office. Of course, all that requires then mask wearing and the necessary COVID precautions. But you can also have that office appointment by Zoom. In this case, again, just send me an email. Say you would like to meet by Zoom at a particular time, and then we will meet at that particular time. Like I previously said, all Zoom classes will be recorded and I will post them on Google Drive. All right, there will also be a few exams. So overall, 4 exams will be held. They are all midterm exams. I will not hold a final exam. All these 4 midterm exams will be before Thanksgiving. So the last week after Thanksgiving, I will still teach some material, but I will not actually test you for that material. So I've already assigned dates. So please mark these dates in your calendar. The first exam will be on September 14th, the second one on October 5th, the third one on October 26th, and the last one on November 20th. So all exams will be held in form of multiple choice course site quizzes, and the exam time will be 50 minutes. Okay, so I will design the number of questions so that you have some time to think about it, but also not a lot of time. Okay, so these questions may not be particularly difficult, but do not expect that you can also think about a long time about them. So in preparation of the exams, I will also assign weekly homework, so that homework will not be graded, so you can do the homework at your own pace and to the extent you think you need them in order to, well, assess yourself how well you can follow the course. So this will be your own responsibility. All right, so this was the organizational part that I wanted to discuss. You can read further details in the syllabus. So I've uploaded the syllabus into CourseSite, so you can find additional details there. But unless there are questions right now, we could actually start with the outline of the course content and then with the first chapter. So are there any questions right at the moment? All right, so no questions. And next, I would like to give you a brief overview over what we are doing in this course. So overall, this is a course which is an introduction into solid state chemistry. So you actually come from different backgrounds. So some of you are chemists, some of you are material scientists, some of you are also chemical engineers. So you have actually probably a fairly different background knowledge in solid state chemistry. I would expect that materials chemists will have the most profound knowledge because materials are most often actually in the solid state in all material science and engineering. Well, requires necessarily a larger knowledge about solid state chemistry already at the undergraduate level. However, I know in the chemistry curriculum, there's only very little solid state chemistry in an undergraduate curriculum. And therefore, the chemists probably don't have a lot of previous knowledge about solid state chemistry. So for that reason, I don't know about chemical engineers in detail actually, but for those reasons, actually, I will start pretty much from the bottom. So for material scientists, some of what I'm teaching will actually not be new, but you will still hear it from a different perspective, from the perspective of a chemist. So I think that even though some of the material may not be new itself, you will hear it from a different angle, and then that can also enhance your education. So the course roughly follows the textbook SMART Moore solid state chemistry. I do not require this textbook. I also do not follow it exactly, but if you want to have a textbook in addition to the lectures and the lecture notes, I would recommend you that textbook, but it's optional. It's also not required for the homework. I will design all the homework questions by myself and will not take them from the textbook. So therefore, textbook is completely optional. So overall, there will be 7 different chapters in this course. I will start with an introduction into symmetry, the symmetry in extended solids. So you will see that in extended solids, there are additional symmetry elements present. In particular, there will be the translational symmetry for crystalline solids and the associated symmetry operations with translational symmetry, namely glide planes and screw axes. So we'll actually extend the knowledge that we probably already have in symmetry for the symmetry of molecules. So symmetry is very important to understand the structures solid state compounds make, but it's also very important to determine the crystal structures. So the state-of-the-art technique, the most used technique to determine crystal structures is X-ray diffraction. So in the second chapter, we will then apply symmetry to X-ray crystallography, and we will see the process of how to determine a crystal structure from an X-ray diffraction experiment using the principles of symmetry. So by this point, you will then have understood, well, how to determine a crystal structure. So in the next chapter, there will be then descriptive solid state chemistry. So in this chapter, you will learn what crystal structures nature actually makes, how we can actually categorize them, and how we can understand them. Meaning, for what reasons does nature make particular crystal structures? Why are some crystal structures very common? Why are other crystal structures comparatively rare? So I will give an overview of that. So once we know our most important, well, solid state structures, we will look in more detail into the chemical bonding of extended solids. So we'll learn about bonding theory, which is an extension of molecular orbital theory, or the chemists of you are probably familiar with molecular orbital theory, but not with its extension, which is called band theory. So essentially, you will learn that when we combine many atomic orbitals in an extended structure, which is containing many atoms, then these atomic orbitals can also be combined to form molecular orbitals, but we call them crystal orbitals then, and we're not getting molecular orbitals, but we're actually getting bands, okay, which are actually molecular orbitals made of many, many atomic orbitals that have very small energy differences. So with the help of this band theory, we can understand the electronic properties of extended solids very well. In particular, if a solid is a metallic conductor, if it's a semiconductor, or an insulator. And we will discuss these electronic properties in the context of band theory. So this way we have covered also electronic conductivity. So in the fifth chapter, then we will discuss ionic conductivity in more details. So solid state compounds cannot only conduct electrons, under circumstances they can also conduct ions. And this is also important for many materials applications, in particular in electrochemical devices like batteries. We actually need an electrolyte. So an electrolyte not necessarily is a liquid, but can also be a solid under certain circumstances. So you will learn what guides ion conductivity, what are the structures that promote ionic conductivity, and by what is ionic conductivity generally affected with regards to structure. So after that, we will have two more special topics. So I will discuss the solid state chemistry of silicates. So silicates are one of the most diverse solid state structures. Silicon and oxygen are actually the most abundant elements on Earth, in the Earth's crust in particular. So pretty much, or almost the entire Earth's crust is actually made of silicates. So in this way, the solid state chemistry of silicates relates also to mineralogy and geology. But because the silicates are so abundant, the silicates also have a lot of materials science applications. Okay, so for example, concrete is all a silicate-based material. Many ceramics are silicate-based materials. For example, porcelain is a silicate-based material. So we will discuss the structures of the silicates. We're classifying them. And then we will also relate these structures to their properties and then their materials applications. In the last chapter, we will then talk in more detail about porous solids. We will see how we can actually make porous solids, why under certain circumstances solid state structures become porous. So porosity and well, chemistry are actually kind of antagonists. So nature likes to fill space most effectively because there are attractive forces between atoms. So we'll see that it actually needs, in many cases, directional bonding in order to overcome these close packing principles to create actually more open structures and porous structures. So these porous structures are technologically very important. They have many applications because they usually have a high internal surface area. So for instance, you can use them as adsorbents for molecules. You will see that based on adsorption, then you can achieve separation for these molecules. But they're also very important in catalysis. So many porous solids have applications in heterogeneous catalysis, and I will give you also an example in that area. Finally, there are also electrochemical applications of porous solids, for instance, in the area of supercapacitors, and we will talk about this a little bit as well. So this is basically the broad overview over what you can expect as part of this course with regard to course content. And again, unless there are any questions, we can start in the remaining time with the first chapter, which will be an introduction into the symmetry of extended solids. So are there any questions right now? Okay, no questions. All right, then let us briefly discuss how can we define solid state chemistry.
Excuse me, doctor. Before we proceed, I think there's a question in the chat.
In the chat, okay. Question in the chat. So,
yeah, I had typed it real quick. I'm sorry, I didn't know if you had your chat up or not. I was just curious, since you are recording these and you said you're putting up to the Google Drive, when would they be available approximately? Are you going to post them like right after class or the next day?
Yeah. So basically, on the same day, you will find them in the Google Drive. Yeah.
Okay, great. Thank you.
Okay. So let us define solid state chemistry. So as the name says, it's the chemistry of, well, matter in the solid state. So we basically need three basic states matter can be in. That's the solid state, the liquid state, and the gaseous state. So when we talk about solid state chemistry, we mean the chemistry of matter in the solid state. So now, when is matter typically in the solid state? Most often matter is in the solid state when the matter is what is called an extended solid. And that means that we have matter which has, well, an infinite structure into at least one dimension, but can be two and most often 3 dimensions. Okay, so basically we have chemical bonding between the atoms in 1, 2, or 3 dimensions, at least on the micrometer scale, or even larger. Okay, of course, no particle can be infinitely large. Okay, so for instance, when you have a sodium chloride crystal, then you have an example of an extended solid. So in principle, a sodium chloride crystal can grow infinitely large, but of course, in practice, there will be restrictions to that. But the particle we are talking about should be at least the size of a micron or larger. Can be also in the order of millimeters, centimeters, or even meter. So it's actually below the micrometer scale. Then we are talking about particles on the nanometer scale. Okay, so if you have a structure in which you have chemical bonding that extends, well, throughout the nanometer scale, okay, either in 1, 2, or 3 dimensions, then you have a so-called nanostructure. Okay, so the nanoscale ranges between, well, 1 nanometer and 1,000 nanometer. So that is 10 to the minus 6 to 10 to the minus 9 meters. Okay, if you go below the nanometer scale, then you're really getting into the order of molecules. Okay, so when we have a molecule, then we are talking about a chemical entity which is held together by chemical bonds, which is finite in all 3 dimensions and is usually in the sub-nanometer scale. Okay, that means 10 to the minus, smaller than 10 to the minus 9 meters. Okay, so now extended solids you find most often in the solid state. Okay, because at room temperature they are, with few exceptions, almost always solid. Only at very high temperature they can melt or they can go into the gaseous phase. Okay, when you have a molecule, then actually that molecule can also be in the solid state. Okay, but you can usually relatively easily melt it or evaporate it, or you can dissolve it. Okay, when you have a nanostructure, you have something in between of that. So also nanostructure can be a solid, but doesn't have quite the property of an extended solid. All right, so here just a few examples that shall illustrate that. So you see here a few polymorphs of carbon. So what are the 2 basic polymorphs of carbon? So these are graphite and diamond. So you see the diamond structure here and the graphite structure here. So now the diamond is the high pressure polymorph of carbon, and the graphite is the low pressure polymorph of carbon. Both diamond and graphite are extended solids. So you have carbon atoms held together by chemical bonds. Okay, and these chemical bonds in the case of diamond extend in 3 dimensions, and in principle the diamond crystal can grow infinitely large. typically diamond crystals are larger than a micrometer. Therefore, we can say that a diamond particle is an example of an particle of an extended solid, a three-dimensional extended solid. So what about graphite? In graphite, you also have an extended solid, but actually only in 2 dimensions, because you have strong chemical bonding only within the graphene sheets. Okay, but the graphene sheets can also extend over a very wide, dimensional range. Okay, you can easily grow them to the micrometer or even larger range. Okay, but we would classify the graphite, in which many graphene sheets are stacked on top of each other, as a 2-dimensional extended solid, because the extension of chemical bonding only extends into 2 dimensions. All right, so there are other polymorphs. You see here the Buckminster fullerene, and you see here the carbon nanotube. Okay, so these are typical examples of nanostructures. So the Buckminster fullerene can still be considered a molecule, but it's already a very large molecule, so that it extends into the nanometer range. Even more so for the carbon nanotube. Okay, but in the case of the Buckminster fullerene, you would talk about a 0-dimensional nanostructure. Okay, while in the case of the carbon nanotube, you would call it a 1-dimensional nanostructure, because the nanostructure extends into one particular dimension much more than in the other 2 dimensions. So now you see here on the very left side adamantane and benzene. Okay, so the adamantane has a relationship to the diamond, and the benzene has a relationship to the graphite. Okay, so you can think the adamantane as the smallest possible diamond particle, if you want to. So if you make diamond particles smaller and smaller and smaller, then you will actually get diamond nanoparticles. And if you make them even smaller, then you will cross the border into the molecular range. And the adamantane would be the molecule which would contain the smallest full set of structural features the diamond has. Okay, so you see here that each carbon is sp3 hybridized, and they're actually, well, here is 6-membered rings. Here, 3 of them that would be isostructural to the rings that you also find in the diamond structure. So similarly, for the benzene, you can think benzene being derived from graphite. So if you take a graphene sheet and just make it smaller and smaller and smaller, okay, containing less and less and less many 6-membered rings, ultimately the smallest entity you can think of is the benzene molecule with only one 6-membered ring of carbon atoms, and the rest being attached to the hydrogen. Okay, so this is just an illustration how molecular structures, nanostructures, and extended solids correlate. All right, so now we have an understanding what extended solids are, how they relate to how they relate to solid state chemistry. Now let us have a closer look at the symmetry of extended solid state structures. So you have probably heard already about symmetry in molecules. So in molecules, you do not have translational symmetry. In the symmetry of molecules, you usually use what is called the Schoenflies notation. Okay? So symmetry in molecules can be used in molecular orbital theory to construct molecular orbitals to explain covalent bonding. And with the help of these molecular orbitals, you can then understand the electronic, optical, and chemical properties of these molecules. So when we look at the symmetry in extended solids, then we will find that we can have, in addition to the symmetry that you find in molecules, also translational symmetry, translation symmetry. So symmetry in extended solids follows, by convention, not the Schoenflies notation, but a notation which is called the Hermann-Maguire notation. So both notations can be used interchangeably, so they're basically saying the same, but they use a different formalism to describe symmetry. Okay, because when we talk about symmetry in extended solids, the Hermann-Maguire notation is typically used. We will use it here in this course too, and if you have not heard about it yet, you will familiarize with it on that occasion. So, like in molecular orbital theory, you can use symmetry in extended solids to construct molecular orbitals. However, these orbitals are then called crystal orbitals that give what is called bands. Therefore, this extension of molecular orbital is then called band theory. Okay, but like you can understand the electronic, optical, and chemical properties of molecules using molecular orbital theory, you can understand the electronic, optical, and chemical properties of extended solids using band theory. So in addition to that, you can also use symmetry in order to determine crystal structures of extended solids using X-ray crystallography. Okay, so in the following, I would like to briefly review the symmetry that you can find in molecules and then talk about in more detail what symmetry in extended solids is under the consideration of translational symmetry. So let us first think about what is symmetry in general. We all have an idea of what symmetry actually is, but how could we precisely define it? So we can define it as the self-similarity of an object. Okay, so for instance, when you look at this butterfly here, you will realize that this butterfly is symmetric because the shape of the left butterfly wing is somewhat related to the shape to the right butterfly wing. Okay, if these two butterfly wings were very different in shape, you wouldn't say that this butterfly is very symmetric. Okay, so symmetry can be defined as the self-similarity of an object. So how can we quantify the symmetry in an object? We can do this by what is called symmetry operations and symmetry elements. So what is a symmetry operation? So So symmetry operation is defined as the movement of an object into an equivalent indistinguishable orientation. Okay, so after that movement, we should not be able to distinguish the object that is produced from the object in its original form. Okay, so when we move that object around what is called symmetry elements. So a symmetry element is a point, a line, or a plane about which the symmetry operation is carried out. Okay, so here in the butterfly, for instance, we have a plane which is called the mirror plane, and we can actually reflect at that mirror plane to move all the objects which are on the left side and belong to the left butterfly wing to the right side, and the right butterfly wing can be moved to the left side, reflected to the left side. So after that movement, after that symmetry operation, we will not be able to distinguish the produced object from the original object. So the two butterflies will look perfectly alike. All right. So here on the right side, you see an example of an ammonia molecule which has a trigonal pyramidal form, and you actually have in this case a line which defines a rotational axis as the mirror plane. So we can actually rotate around this axis until the two hydrogen atoms here will superimpose again. Actually, we have to rotate by a 120-degree angle in this case. So after we have carried out that symmetry operation, the produced NH3 molecule will look perfectly like the original one. Okay, we could superimpose them. Also, we could not distinguish them. Okay, so now what symmetry operations do we know? What symmetry elements do we know? So the first one and the most simple one is the so-called identity operation. Okay, so the identity operation says nothing else but that each object is self-similar to itself when you do nothing with it. Okay, so that's of course trivial, but mathematically one needs that identity operation to make the mathematical theory behind symmetry, which is called the group theory, complete. Okay, so we should never forget that the identity operation actually exists. So you may know that for the identity operation, the Schoenflies symbol is a capital letter E. So the respective Hamann-Maguire symbol is actually a simple 1. So this 1 is chosen for a reason. Actually, these numbers, they represent the order of principal rotation or of proper rotational axes, which we'll discuss next. And in order 1 means that you rotate by 360 degrees Celsius. Okay, so when you rotate an object by 360 degrees, not Celsius, just 360 degrees, then all the points in that object are in their original position, right? So when you rotate on 360 degrees, it's as though you do not rotate at all, okay? So it's as though you would do nothing with the object. And therefore the 1 is an appropriate symbol to express the identity. Okay, so next, let us look at proper rotations. So in the Schoenflies formalism, they are symbolized by a capital letter C with a subscript N. So N represents the order of the axis of the rotation. Okay, and the order of the axis is defined by the angle around which you rotate. Okay, and the angle is nothing else but 2 pi or 360 degrees over n. Okay, Okay, that means that if you rotate by 180 degrees, the order of the axis is 2, and that n here becomes 2. When we rotate around 120 degrees, then the order is 360 over 120, which is 3, and so forth. So the Hermann-Maguire symbol is just n, okay, whereby n represents the order of the axis. So when n is equal to 1 means that we rotate around 360 degrees, then that's actually the same as the identity. When n is equal to 2, it means that we rotate by 180 degrees. When it's 3, that means that we rotate around 120 degrees. Okay, so for instance, in this molecule here, BF3, we have, well, 3 fluorines that surround the boron in a trigonal planar fashion. Okay, and there is a threefold axis, an proper axis with an order n equal to 3, which goes through the boron atom here and stands perpendicular to the plane. Okay, so as we rotate by 120 degrees, then the fluorine atoms here exchange their positions. The boron atom doesn't change its position, but as the fluorine atoms move around, they produce the molecule in an indistinguishable form, which is superimposable with the original molecule. So now it is a property of a proper rotational axis that when you carry out the symmetry operation n times, then that produces the identity. Okay, so for instance, when we have a C3 axis, a threefold axis, then after carrying out the symmetry operation C3 3 times, then that's the same as the identity. So why is that? Because when we rotate 3 times around 120 degrees, then that is the same as rotating 360 by 360 degrees, and that is the same as the identity. Okay, so if the axis was 4-fold, then we would have to rotate 4 times by 90 degrees, and again that would give 360 degrees, producing the identity. So a particular molecule can have multiple proper rotational axes, and the axis with the highest order is called the principal axis. Okay, so for instance, that B3 molecule here, in addition to the C3 axis that we just discussed, also has C2 axes. Can you see them? Well, there are actually 3 of them. Each of them go through a BF bond. Okay, so there's one here, there's one here, and there's also one over there. So what happens as we rotate around these axes? Well, the fluorine molecule, which is on the axis, doesn't move. The boron also doesn't move, but the 2 Fs here exchange their position. Okay. Again, we have produced a molecule which is indistinguishable from its original form. That proves that this symmetry element exists. Okay. So the C2 axes, 3 of them we would have overall, would not be the principal axis. The C3 would be the principal axis because it's the axis with the highest order. Okay. So then the next symmetry operation is the reflection operation. Okay. So the Schoenflies symbol for a reflection operation is sigma. In the Hermann-Maguire formalism, the symbol is M, okay, whereby M stands for mirror plane. Okay? The mirror plane is the symmetry element associated with the reflection operation. So the Schoenflies formalism knows distinguishes between three different types of mirror planes, so-called vertical mirror planes, dihedral mirror planes, and horizontal mirror planes. The Hamann-Marguerat symbolism doesn't do that. In this formalism, all the mirror planes are not distinguished. Okay, so they're all getting symbol M. So, so for instance, in the BF3 molecule, we have a mirror plane here, which is in the plane of the molecule. So now as we carry out the symmetry operation, you will notice that, well, the atom positions don't change. So the fluorines, they stay where they are, and the bond stays also where it is. This does not, however, mean that this mirror plane doesn't exist, because the actual criterion is whether any points move through space to another position. Okay. So why do points in space still move? Well, we can understand this when you're considering that each of these atoms are actually spheres. Okay. And well, one half of the sphere lies above the mirror plane, and the other half of the sphere lies below mirror plane. Okay. Therefore, each point on the sphere which lies above the mirror plane will be below the mirror plane, and vice versa after the symmetry operation has been carried out. So now, in addition to that mirror plane here, you actually have three others noticed here, and these go to the BF bonds. Okay. So when we have multiple mirror planes, then we count them, but we actually do not write number symbols, because we could mix them up with principal axes, which have also number symbols. So therefore, we always write out actually the word for the number. So we write actually 3M instead of using the mathematical symbol for 3. So in the Hamann-Marguerat formalism, we do not distinguish between that kind of mirror plane and these three mirror planes. In the Schoenflies mechanism, we do. So these three mirror planes are actually called vertical mirror planes, and that here is called a horizontal mirror plane, which we would call sigma h and sigma v and sigma h respectively. So I just want to briefly review how a vertical and a horizontal mirror plane is defined. So a horizontal mirror plane is defined as a mirror plane that stands perpendicular to a principal axis. So keep in mind that the principal axis in our BF3 molecule is a C3 axis, which stands perpendicular to this plane. Okay, therefore, this plane here, which is a mirror plane, is a horizontal mirror plane. It stands perpendicular to the C3 axis. Whereas these three mirror planes here, they contain the principal axis. And if they contain the principal axis, then they are called a vertical mirror plane. There's also a third mirror plane, which is a special form of a vertical mirror plane that's called a dihedral mirror plane. When we have a dihedral mirror plane, then that means that the mirror plane actually bisects the angle between two C2 axes. Okay, but this is only necessary to know when we use the Schoenflies mechanism formalism, not when we use the Hamann-Marguerat formalism. All right, so we have started 3 minutes late, so now it's already 3 minutes over the time. Therefore, I think we can just stop here, and we will discuss more symmetry elements and more symmetry operations later. And I will just stop the recording now. Stop recording.